there is an organic chem practice. So I don't know if you all can see what I'm seeing here. I don't know how to zoom in. Anyways, there's an organic chem practice, this file right here. Alright, if you'll go to this file, then this worksheet. This is the worksheet I'm talking about. So this worksheet has a bunch of things, but what you all want to use is some of the practice like addition reactions, substitution reactions, things like that. Now this doesn't have mechanisms, but you guys can go through some of these and look for any questions on substitution, like alcohol dehydration, what's in reactants, products, and catalysts, like things like that. You all can use that as sort of a, what do you call it, process, right? So I know that seems like a lot of work because you have to go through and see which questions apply. I didn't bother even like trying to give you all this practice, but just so that we.
So you got the answer sheet so we could check, or you got like the answer sheet so we could.
The answer sheet is at the end. Oh. So all the answer sheet is at the end. Alright. So that's just what I wanted to do. Alright. Alright, folks. So today we're going to finish off the addition of alkenes. Alright, and we have different ones. We talk about hydrogenation, and we'll talk about some of the other ones in that. Alright, so hydrogenation is pretty easy, right? The things that we have to remember for hydrogenation, we have a few things. First thing is, these are the catalysts. Just remember those are the catalysts that we use for hydrogenation. It's pretty straightforward. Remembering those platinum, palladium, or nickel, and that just means that once we have hydrogen present, we make all our double bonds single bonds. Right? So that's the main thing. So those are the main catalysts. So there's no trick or anything like that. Simply know that if we have platinum, palladium, or nickel, we hydrogenate our alkenes, right? And the other main thing that you also write down is that it's always syn addition. So syn addition means what? What does syn addition mean? Same side, right? So it's an adding on the same side of the carbon-carbon bond. So whenever we add our hydrogens, remember whatever is there. So say for example, these two were like methyl groups, they would be pushed up or pushed down. But you would change you would keep the steric temperature as if they're all both attaching at the same side. So syn addition, which we talked about already. Alright. So let's look at the mechanism. It's not really a mechanism, it's honestly just it's like an enzyme. So you all have done enzymes, you all talked about enzymes in biology, right? In biology, how enzymes work is that you have a surface of the enzyme, right? Is this familiar? Is this not familiar? For an enzyme? Have you all not done enzymes in biology? Oh, shut up, right? I don't know. Even in high school, you talk about enzymes. Alright, so when we talk about enzymes, we have a surface of the enzyme, right? It's the same way as a catalyst. The surface, the hydrogens attach to the surface, and then the double bond, the pi bonds, the p orbitals, will attach to the surface as well. So the p orbitals is what is attaching to the actual surface of the catalyst, right? When that happens, by some magic, this hydrogen moves over and then bonds to this carbon. When that happens, there's a hydrogen that's left, and then there's sort of like a carbon that needs a bond, and the hydrogen goes to that one. Simple as that. It's magic. Like a lot of catalysts, you don't know exactly how they work, but they work. Alright, so just imagine syn addition happening. You have the double bond, the hydrogen is already. So, okay, the order of this hydrogenation order is this, is that you saturate platinum catalyst, or whatever the catalyst you use, with H2 gas, right? So hydrogen attaches to our platinum surface, right? So you saturate the surface with platinum, and then you have the alkene attaches to the surface. I mean, I don't want to, you don't have to write this down, but I know once I write stuff on the board, you'll write it down. But, I just kind of want to show the order. It's literally right there, but I'm just writing it in different ways so that we kind of remember it. So you saturate your platinum catalyst, then the alkene attaches to the surface, and then a hydrogen attaches to one carbon of alkene, right? And then you have the second hydrogen attached to other carbon of alkene, simultaneously leaving. Alright, so you get a simultaneous leaving of your alkene from the surface. Alright? So that's sort of the thing that's happening. So main things, like I said, know what catalyst, and then know that the fact that it's a syn addition, so your stereochemistry is going to reflect that. Alright? So already, this is all the things that I said. So hydrogen absorbed to metal, hydrogen inserted in the same place as that one. All that. Syn, stereochemistry. Alright, that's it for hydrogenation, nothing else. And we'll look at some examples and see you guys will. Alright. So now here is the main thing that we talk about. First main type of mechanism. Alright, epoxides. Epoxides. For your write anything down, where have you all seen epoxides before? We use epoxides. Epoxy glue, right? Epoxy glue is a very binding glue, right? And the reason is that once you open up an epoxide, it binds quickly, right? It binds readily to your surface. So it's a really good compound for us to sort of bind it. So you separate it into tubes and then you have a reaction. But the main thing you have to understand is that whenever we make an epoxide, we use what we call a peroxy acid. Alright? We use a peroxy acid with an alkene. And I don't know if I've mentioned this before, but peroxide. So a peroxide, so anything that has an oxygen to oxygen bond is a peroxide. So anything with an oxygen to oxygen bond is a peroxide, right? And one thing you have to remember, the reason peroxides are used so much is that this oxygen to oxygen bond is extremely weak. Alright? So we make a very weak oxygen to oxygen bond, right? And usually that oxygen to oxygen bond goes through homolytic cleavage, meaning that you break the two electrons that are forming that bond separate like half and half, right? It's not one. But when you do this epoxidation, it's not going to be a homolytic cleavage, it's sort of going to be like an insertion, right? So we're going to talk about the fact that we're actually inserting a bond in replace of this oxygen-oxygen bond, right? So that's what we're going to look at, right? Alright, so I'm going to say words like concerted, like insertion, like peroxidation, stuff like that. Don't get confused. Very simple. Alright, if you feel confused, just ask me a question and I'll try to explain, right? So, right, so we have a peroxy acid, making epoxide, and an acid as it, right? So, the most common reagent that we use, the most common peroxy acid that we use is peroxybenzoic acid. Right, it's peroxybenzoic acid. And you always see an example of it. Reason we use this so much is because when this bond breaks, it's easily stabilized by the benzene ring. Right? So that's why we're going to use that as a reagent. So let's look at the reaction. So this is a concerted mechanism. Concerted meaning that we don't have steps. It's all going to happen in one transition state. Right? So if I were to draw this energy diagram, it would simply look like this. The energy diagram would just look like that's the energy diagram for a epoxidation because it's just one transition state. There's no intermediate formed or anything like that. It's one step, one transition state when we talk about this mechanism. All right. Main thing is looking at the flow of electrons. Right? It's looking at the flow of electrons. So let's identify electrophiles and so forth, right? Alright. So if I look at this sort of mechanism, usually I told you find the electrophile, find the what do you call it? The nucleophile, right? In this case, because it's a concerted mechanism, we don't really have nucleophiles and electrophiles. But I want us to kind of understand where electrons are flowing to. So because of this thing, you'll notice electrons are sort of flowing away from that oxygen, right? And the reason being is that oxygen that's there is a weaker bond, right? It's a weaker bond between the other two oxygens. So electrons are starting to flow away from that oxygen, right? So remember, this hydrogen has electrons flowing towards itself, towards that oxygen. So as this oxygen becomes more positive, it allows for attack from this alkene. So this now acts as our nucleophile, right? So the alkene goes and attacks that oxygen, and then electrons start to move. And as electrons move, you notice that this is starting to make a bond here, right? So this is sort of the first bond that's starting to make, while this bond is starting to break. So if you look at, let me clear some of this thing. So if you look at this drawing, anything that's in green is a bond that's breaking. Anything that's in red is a bond that's forming, right? So what is happening is that as the oxygen is breaking its bond with the other oxygen, the alkene is formed, the carbon is forming a bond with that oxygen, and then it starts to form other bonds. So now you notice this right here, this right here is now about to make the carboxylic acid or the carbonyl right here, right? So that bond is starting to form. And the reason the benzene peroxide, the benzoic acid works is because the R right here helps stabilize our formation of that double bond, right? And then that bond between carbon and oxygen is going to break, and then you end up with a OH group. And then, if you look at this, this right here goes from becoming a nucleophile, and as this bond breaks with hydrogen, now becomes an electrophile. Goes from becoming an electrophile and becomes a nucleophile. Sorry. Alright. So basically what we're looking at is oxygen 1 here first becomes an electrophile, accepting electrons. When it comes to this point, it becomes a nucleophile, and then making or tackling that. So this is nucleophile, this is electrophile, this is nucleophile, this is the electrophile. Now we don't actually make nucleophiles and electrophile, it all happens in one step. But if you look at the flow of electrons, the flow of electrons sort of run like a circular motion, right? So your job is to remember that conservatively. That transition state, that's sort of your job. Knowing what is positive, what is being added, what's being broken. Alright? And that's it. Alright. So benzene peroxide acid, so one step we talked about that. And this is the name of the peroxide acid. So it's meta-chloroperoxybenzoic acid, or MCPBA. You'll have to remember that name. MCPBA, meta-chlorobenzoic acid. Can somebody draw that? Can you all draw that? What does that look like? No? Imagine this is your peroxide acid here. And the R group is just a benzene with a chlorine on it. That's it. Okay. So meta-chlorobenzoic acid. Okay. So MCPBA, that's it right here, acts as our catalyst, and we use it, well, not a catalyst, it's the substrate that we attach to this alkene, and we form our peroxide. Now the stereochemistry, right? If you'll notice, this carbon-carbon double bond is being broken and formed on one side, all right? So it's sort of like a syn addition, right? So whatever is here is going to move to one side. So whenever you form it, you're going to basically take the hydrogens or whatever. All of this comes to one side. So it's all on one side of the double bond, right? And then with the trans, it's the same thing, all on one side, but you have groups of things. So it's the same thing going on. And we have this dichloromethane, because I like to this dichloromethane is just a solvent. Epoxides. So now we can use epoxides to then make alcohols. So you can use an epoxide to make an alcohol by using water. So in the presence of water with an acid, you can make a diol. So this is now the beginning of the diols that we'll talk about. So you can make a diol using water and acid catalyst. If you look at the mechanism, the proton, the oxygen that's on the epoxide attaches a proton, right? It becomes this sort of positively charged substance. Water then goes and attacks the opposite side of the epoxide and attaches itself on the opposite carbon. Now, what type of addition is this? What's this type of addition? Anti. Right? If it's not on the same side, it's opposite sides. This is anti-addition. Right? So for you to make the diol, you have to first make the epoxide and then add water, and you make this anti-addition diol. Alright? Once you make the anti-addition diol, then the water takes the proton and you get your diol. Right? This is actually the only way to make an anti-addition diol. Right? We're going to see some other diols, but all of those other diols are made using syn addition. So now let's look at the syn addition of the alkenes. So this is now making alkene and converting it to a diol on the same side. So again, just so that we remember, the only way we make anti-addition at diols is using an epoxide ring. they give me the steps to go to make this. You have to show me how do I go from this alkene to this anti-addition diol. Alright? So this doesn't happen in one step. This you have to make the epoxide first, so you have to show what you do to make the epoxide, and then once you make the epoxide, then you have to show that you can make the anti-addition diol, right? So I just wanted to clarify that so we understand that, right? So now the syn addition is sort of simple, it's easier, it's one step. So with syn addition diols, we use two reagents. You can use either osmium oxide, osmium teroxide, or, and this is important, cold dilute KMnO4. Alright? So, real important. Potassium permanganate, guys, is a strong oxidant. So instead of forcing the diol to become this like carboxylic acid, you have to make sure when you do this reaction for KMnO4, you do it in a cold solution and a very dilute solution. Right? That's super important. Because if I say warm and hot, then you know it's not going to make a diol, and we'll see what else it makes. Alright? So everybody have those two reagents. If I want to make the this one, which is the syn addition, I don't have to use the epoxide ring. Right? I can simply just do like osmium teroxide, or I can use cold dilute KMnO4. Right? And the osmium oxide, we're going to have to use a peroxide at the end of it, but that's sort of the focus, right? Alright. I hope you're all making flashcards. So let's look and see what happens. So this again is a concerted mechanism. Right? So this is a concerted. So from this step to here is one transition state. Right? And the transition state is this sort of concerted. Remember I said we're going to use that word a lot, concerted formation of this compound. So this is an ester, but this doesn't give us our diol. So in order to get the diol, we have to treat it with hydrogen peroxide. Right? So we make this first, and then you treat it with hydrogen peroxide to get our diol. Right? And you get back the osmium oxide, teroxide. Pretty straightforward. Again, it's a conservative mechanism, and you have to make sure it's hydrolyzed using the peroxide. Now, you don't need to show the mechanism for how the peroxide makes this. It's pretty straightforward. It's sort of like the bonds breaking and the hydrogen sort of get clipped. But that's basically the mechanism. That's what those slides before. When you do a problem, if we have a problem, like the example. This is from here to the anti, you have to we show the epoxide already, and then you just show a time. So if we have time to go over that. Right. So then the other one, so again, this mechanism, if I use potassium permanganate, we're just going to have this. So imagine the same thing, but except for the manganate, right? And then you don't have to treat it with peroxide. It sort of breaks itself in the presence of a base, right? So the base is what, so it's the same thing but really manual. Now, let me tell you all something. For the most part, we do not make diols with potassium permanganate in actual practice, because it's so easy for that to oxidize those hydroxyl groups to carboxylic acids. So now another way that we can make or we can sort of break carbon-carbon bonds or oxidize is using ozonolysis. Now the benefit of ozonolysis is that we make aldehydes and ketones. Alright? So if I want to make an aldehyde and ketone from an alkene, I will use ozone. Right? So this is breaking. So the main thing is there's oxidatively cleave or break the double bond. Alright, so we're actually going to break this double bond, ladies and gentlemen. Let's go over it. Alright? So whenever you make this, whenever you use ozone, you actually break the carbon-carbon bond. Alright? And that happens through a mechanism where ozone again is another conservative mechanism. Right? Ozonolysis is a lot milder. We don't use, if you use KMNO4, it's going to oxidize our aldehydes. Alright? And aldehydes become carboxylic acids. Alright? So we don't want to do that. So it's really mild. And the second step of the ozonolysis is literally reducing it using some sort of metal, usually dimethyl sulfide, because we make this ozonide. So with ozone, we make ozonide, and then we have to reduce this, meaning take off some of this oxygen-oxygen bonds, and make our aldehyde or ketone. Alright? I want to get through these mechanisms because I want to summarize all our reactions, right? So you can kind of see. Alright. So this is a similar mechanism, guys, to sort of this concerted mechanism. So again, the oxygen, one of these oxygens attacks the carbon, then it forces the double bond to attack another oxygen, and the electrons just keep moving around, right? From here to here is what usually confuses me, alright? So this is a bunch of magic. I don't know what it is. So first it goes in this direction, right? So it goes in a clock, this one anti-clockwise direction, and then it goes back in the other direction. So if you all see this is going in this direction first. Once it's formed, then it goes back in the opposite direction, and then it goes back in the, so it goes like, if you all look at it, this is going anti-clockwise, then clockwise, then back anti-clockwise. So it's going like negative, positive, right? So it goes back and forth, and that back and forth eventually ends up to our ozonide here. Now, in organic chemistry, for those of you all who ever do organic chemistry after this, these mechanisms are literally theories, right? What happens is, when they use ozone on an alkene, they ended up getting a compound that looked like this, right? So what the people who come up with these mechanisms do is they said, okay, we got this, right? When we added the ozone. So why is this oxygen in between these carbons, and why do these oxygens exist like this? So they go through some possible ways to do that. So that's how they got up with this jumbless right here. So they go through and do some experiments and try to guess what it looks like. So it's sort of like, I don't like this mechanism, to be honest. I find it's a little almost like gibberish. But anyways, basically you want to take this double bond, and the main thing I want you to think about is that you're inserting, right? We're going to insert this carbon oxygen, one of these oxygens, in between. So what happens is you have a carbon bond, and you want to insert an oxygen in between them. Alright, so whenever you think of ozonolysis, think of making this carbon-carbon bond and then inserting an oxygen in between them. Alright, and then also having this like this. So anytime you think of epoxidation, think of putting an oxygen in between the two carbons. Alright, and then you also have this peroxide bond here, but you want to put the oxygens in between the two carbons. Alright? And that's sort of where we get our osmosis. So this mechanism I'm not too thrilled with, so I don't usually make your drawers, but maybe it all to you all have to. Alright. So that's the first step, to make the ozonide. Once you make the ozonide, then you just, there's no mechanism you all have to remember. The dimethyl sulfide is just a substance you have to remember. That dimethyl sulfide reduces, the word reduce. So this is reduction. Right? Remember, you're reducing it. So you reduce the oxygen bonds into ketone and aldehyde, right? Depending on what's attached. Right? If this was another R group, then it would be 2 ketones. Simple as that. Right. So dimethyl sulfide usually acts as the atom to oxidize, and it oxidizes into DMSO. DMSO is a solvent that we use in NMR, so we use it a lot for actually identifying other, like dissolving certain substances. It's very good at dissolving a lot of organic. This dissolves a lot of organic material. So you don't have any fingers. Alright. So let's go through our problem. Alright? And try and figure out what do we get. So I want you all, right, write down your notes. These are the two products. Right? These are the two products. Draw the original alkene that would make these two products using ozone, using ozone. So go ahead and draw what this would be like